Imagine a disaster moving toward Earth right now. Not in 1,000 years. Not in 1,000,000 years. Right now. At this exact moment, as you watch this, as you breathe, as your heart beats, something is approaching. And there is absolutely nothing anyone can do about it. Not because we lack the technology to respond. Not because our instruments aren't sensitive enough. Not because our scientists aren't smart enough. But because warning is physically impossible. Any signal that could tell us it was coming would travel at the speed of light. And the thing itself travels at the speed of light. Which means the first indication that it exists would arrive at precisely the same moment as the thing itself. There is no gap, no window, no last moment of awareness, no final second to understand what is happening. You would not see it coming. You would not feel it coming. You would simply be here, and then the rules that allow you to be here would be gone. This is not science fiction. This is not a thought experiment invented to frighten people. It is a real and legitimate possibility that emerges directly from our best understanding of quantum mechanics and the fundamental nature of the universe. It has been discussed seriously by some of the most respected physicists who have ever lived. Stephen Hawking wrote about it. The discovery of the Higgs boson in 2012 made the conversation more urgent rather than less. And it has a name: vacuum decay. Now that the term has a context, now that you understand what it means before you know how it works, let's follow the logic, because the horror of vacuum decay doesn't come from what it is. It comes from what it implies. And what it implies is something the universe has never given us any tool to argue against. Let's start with the ground you're standing on. Not the physical ground. Something deeper. The quantum ground. In physics, the vacuum is not empty. That is one of the most counterintuitive and most thoroughly confirmed facts in all of science. Empty space, the space between atoms, the space between planets, the space between galaxies, is not nothing. It is a seething, fluctuating field of quantum energy. Particles appear and disappear on timescales so brief they cannot be directly observed. Energy rises and falls constantly at the smallest scales of reality. The vacuum has a structure. It has properties. It has what physicists call an energy state. And here is the question that changes everything. Is that energy state the lowest possible one? Think of it this way. Imagine a ball sitting in a valley. The ball is at rest. It appears stable. But the valley it's sitting in is not the lowest point in the landscape. There is a deeper valley further along, a lower energy state that the ball hasn't reached yet. The ball appears to be at rest. It appears to be stable. But it is not in its true ground state. It is in what physicists call a false vacuum. A temporary configuration that looks stable, but isn't. Given the right conditions, given a sufficient push, the ball would roll over the barrier between valleys and fall into the deeper one. And in doing so, it would release the energy difference between the two states. Now, apply that picture to the vacuum of space itself, to the quantum field that underlies all of reality, to the ground state of the universe. What if the universe is the ball in the higher valley? What if the energy state of the vacuum, the configuration that allows atoms to form, stars to burn, matter to exist, and life to arise, is not the lowest possible energy state? What if there is a deeper valley? A true vacuum with lower energy than the one we currently inhabit? And what if the barrier between our false vacuum and the true vacuum can be crossed? Not through a gradual process, not through slow decay or steady erosion, but through quantum tunneling. Quantum tunneling is one of the strangest and most confirmed phenomena in physics. At the quantum scale, particles do not need to go over barriers. They can go through them. A particle with insufficient energy to classically cross a barrier can simply appear on the other side of it with a probability that depends on the height and width of the barrier. This is not theoretical. It is the mechanism behind nuclear fusion in the sun, behind the operation of transistors in every electronic device you own, behind radioactive decay. Quantum tunneling is real, it is measurable, and it happens constantly at the smallest scales of the universe. And it can happen to the vacuum itself. At any point in space, at any location in the universe, at any moment in time, a quantum fluctuation could tunnel through the barrier between the false vacuum and the true vacuum. A bubble of true vacuum, smaller than a proton, could spontaneously appear. And the moment it appeared, the laws of physics would be different inside it. The energy state would be lower. And the boundary between the true vacuum inside the bubble and the false vacuum outside it would be unstable in exactly one direction. Outward. Always outward. At the speed of light. This is the bubble. And understanding what the bubble actually is, what it means, what it does, what it leaves behind, is where the horror moves from abstract to absolute. The bubble expanding outward at the speed of light is not a wall of fire. It is not a shockwave. It is not an explosion in any sense that the word usually implies. It is something categorically different and categorically worse. It is a boundary between two sets of physical laws. On one side, our side, the laws of physics as we know them. The laws that allow protons and neutrons to hold together. The laws that give electrons their mass and their charge. The laws that govern every interaction between every particle that has ever existed in our observable universe. On the other side, inside the bubble, a different set of laws entirely. Laws determined by the lower energy state of the true vacuum. Laws we cannot predict, cannot calculate, and cannot survive under. Inside the bubble, the fundamental constants of physics would be different. The mass of the electron might be different. The strength of the electromagnetic force might be different. The relationship between energy and matter that allows atoms to be atoms might simply not exist. Chemistry as we know it would be impossible. Biology would be impossible. The specific configuration of matter and energy that produces stars and planets, and the conditions for life would be gone. Not destroyed. Not converted into something else. Simply incompatible with the new rules. The bubble doesn't kill you. It deletes the conditions under which you can exist, and it expands at the speed of light, which means no part of the universe that it reaches has any warning, any preparation, any awareness of what is coming. The edge of the bubble is the first and last thing anything in its path would ever encounter. And because nothing travels faster than light, nothing inside the bubble's expanding perimeter can ever send a signal outward to warn what lies ahead. The universe ahead of the bubble continues normally. Stars shine. Planets orbit. Life, wherever it exists, goes about the business of existing. And then the edge arrives. And then the rules change. And then there is nothing where there was something. No explosion, no warning. Just absence. Now, here's where the angle becomes the thing that should genuinely keep you up at night. We do not know whether this has already happened. The universe is 13.8 billion years old. It contains hundreds of billions of galaxies, each containing hundreds of billions of stars, distributed across a volume of space so vast that the numbers lose meaning for human intuition. And in any region of that space, at any point in the last 13.8 billion years, a vacuum decay event could have begun spontaneously. A bubble smaller than a proton appearing in some unremarkable corner of an unremarkable galaxy, billions of years ago, now expanding at the speed of light in every direction. If that happened, if vacuum decay began anywhere in the observable universe at any point in cosmic history, the bubble is out there right now, expanding, growing, consuming everything in its path, converting false vacuum to true vacuum at 186,000 miles per second in every direction simultaneously. and we would have no way of knowing. Not because our telescopes aren't powerful enough, not because our mathematics isn't sophisticated enough, but because the information that a bubble exists cannot travel faster than the bubble itself. The bubble is its own announcement. By the time we could know it existed, it would already be here. This is the logical trap that has no exit. In a universe where vacuum decay is possible, and our best physics says it is, there is no observation we could make, no measurement we could take, no experiment we could run that would tell us whether a bubble is currently expanding somewhere in the universe. Our observable universe could be completely bubble-free. Or a bubble that began 3 billion years ago could be 1 billion light years away and closing. The night sky would look identical in both cases. The stars would shine with the same indifference. The CMB would register the same ancient temperature. Everything would appear completely normal right up until the moment it wasn't. There is a version of this story in which nothing happens, in which the vacuum is stable, has always been stable, and will remain stable for timescales that dwarf the current age of the universe. Physicists who have studied the Higgs boson mass and the stability of the electroweak vacuum suggest that our vacuum may be metastable, sitting in a false vacuum but with a barrier high enough and wide enough that the probability of tunneling is vanishingly small on any human timescale. Perhaps on any timescale we can meaningfully imagine. But here is the thing about vanishingly small probabilities. In a universe this old and this large, a probability that is vanishingly small per unit volume, per unit time, becomes a certainty if the volume is large enough and the time is long enough. And we have no idea how large the universe actually is beyond our observable horizon. We have no idea how much volume there is for vacuum decay to sample. Inflation, as we discussed, implies a universe incomprehensibly larger than our observable bubble. In a universe that large, even an extraordinarily small probability per unit volume becomes something that has almost certainly occurred somewhere. The universe may be stable enough that nothing happens for trillions of years in our local region, and it may have already ended somewhere else billions of years ago. Both things can be simultaneously true, and we cannot distinguish between them. But here is the final implication that almost nobody talks about when this topic comes up, the one that reframes everything. The laws of physics that currently govern our universe, the specific values of the fundamental constants, the specific relationships between forces and particles, the specific configuration of quantum fields that allows matter to be complex, chemistry to be rich, and biology to be possible, are not inevitable. They are not the only possible laws. They are the laws that happen to correspond to our current vacuum state. And if our vacuum state is not the ground state, if there is a lower energy configuration that physics will eventually find its way to, then everything that exists, everything that has ever existed, everything that will ever exist inside this observable universe is temporary, not in the ordinary sense of lasting a long time before ending, but in the deepest possible sense. We are structures that exist because the rules currently permit us. We are patterns in a field that has not yet found its lowest energy configuration. We are, in the most literal physical sense, living in a universe that has not finished settling, and we have no way to know how much settling remains. If you are the kind of person who finds that the deepest questions are the ones that offer no comfort, that the most honest answers are the ones that leave the most unresolved, then Cosmora is exactly where those questions live. Subscribe and stay. There are more unsettling truths ahead, and we are nowhere near the bottom of them. But before we close, here is the thought that belongs to you now. Step outside tonight. Look up. Find the darkest part of the sky and look at it long enough for your eyes to adjust. You will see stars. You will see the faint smear of the Milky Way if the conditions are right. You will see the universe going about the business of existing. burning, expanding, indifferent to your presence and your questions. Everything you can see is still here. Every star still shining. Every galaxy still turning. The observable universe is intact and unchanged, and as ancient and vast and indifferent as it has always been. But intact is not the same as stable. Still here is not the same as safe. And unchanged is not the same as guaranteed. Somewhere in the darkness between those stars, in a direction you cannot determine, at a distance you cannot calculate, moving at a speed nothing can outrun, there may be a boundary, a clean geometric edge where the rules change, where the stars on the far side simply stop, not because they burned out, not because they were destroyed, but because the conditions that allowed them to exist no longer apply on the other side of a line that is getting closer at the speed of light. Or there may not be. The universe may be stable, completely, permanently, indefinitely stable. The night sky you are looking at may be exactly what it appears to be. Ancient, vast, and quietly eternal. The physics cannot tell you which one is true. The mathematics cannot distinguish between them. The most powerful telescopes ever built look at the same sky and return the same answer. Everything appears normal. And that, right there, is the most unsettling sentence in all of science. Not because it tells you something is wrong, but because it tells you absolutely nothing at all.